there seems to be something amiss in our understanding of the universe. Cosmology is currently facing a major dilemma regarding one of its most fundamental questions. How fast is the universe expanding? For over a decade, two different methods of measurement have been at odds. Observations of the present universe suggest that its expansion rate, known as the Hubble constant, is about 9% faster than expected based on early universe data. Scientists had hoped the James Webb Space Telescope, the most advanced telescope ever created, would help resolve this discrepancy. However, so far it has not done so. In fact, Webb's incredibly precise new observations have reinforced the issue, complicating the standard model of cosmology. The question now arises: could the physics that govern our universe need to be revised or even replaced? This has become a topic of intense debate, as scientists face the possibility that there is something fundamental about the universe that we do not yet understand. Join us as we dive deep into the new ultra-deep images from the James Webb Space Telescope, which have recently confirmed that we might be missing something crucial in our interpretation of the universe. The universe, according to the widely accepted model, began with a Big Bang, where energy, mass, and space came into existence all in an instant. This was followed by the formation of a hot, dense plasma of matter and antimatter particles that collided and annihilated each other. However, for reasons that remain unclear, a slight imbalance allowed more matter to survive than antimatter, preventing the universe from collapsing in on itself. As gravity compressed this plasma, the matter was heated and sound waves traveled through it at half the speed of light, creating what is known as acoustic oscillations. Meanwhile, the high-energy density of the early universe expanded space-time, causing pockets of mass to be pulled apart. As the universe continued to expand, ordinary matter, which interacts with light, began to coalesce around invisible dark matter, forming the first galaxies, all connected by a vast cosmic web. As the universe expanded, its energy density and expansion rate decreased. However, about 5 billion years ago, galaxies started to move apart again, at an ever-accelerating rate. The cause of this acceleration is a mysterious force called dark energy. Dark energy is often explained as a cosmological constant, a uniform energy field woven into the fabric of spacetime itself. Albert Einstein first introduced it in his theory of general relativity and called it lambda. As the universe expanded, the density of normal matter decreased, while the density of dark energy remained constant. This made dark energy the dominant force driving the accelerated expansion of the universe. Together, normal matter, and dark energy are the key components of the lambda cold dark matter, lambda CDM model, which not only describes the universe's expansion but also predicts its eventual end in a big freeze, where all matter is spread so thin that the universe becomes cold and dark. However, there are significant problems with this model. Despite many successes, scientists still do not understand what dark matter or dark energy are. As Professor Ofer Lahav from University College London, a cosmologist involved in dark energy studies, points out, while it is widely agreed that the universe consists of 5% normal matter, 25% dark matter, and 70% dark energy, we have little understanding of the latter two components. An even greater challenge to the lambda CDM model has emerged in recent years. Depending on the method used to measure it, the universe appears to be expanding at different rates. An inconsistency known as the Hubble tension. Measurements based on observations of the early universe show it expanding significantly faster than the lambda CDM model predicts. These measurements have been confirmed by countless observations. As Nobel laureate Adam Rees, who led a team that made new measurements with the James Webb Space Telescope, states, the only explanation he can find for the discrepancy is that our current model might be missing something crucial. There are two primary methods used to measure the expansion rate of the universe. One looks at the cosmic microwave background, CMB, a remnant from the early universe, created just 380,000 years after the Big Bang. The CMB shows temperature fluctuations that provide clues to the density of matter and energy in the early universe. By studying these fluctuations, scientists can estimate the Hubble constant. The European Space Agency's Planck satellite measured the CMB with incredible precision between 2009 and 2013, providing a value for the Hubble constant of around 67 km per second per megaparsec. To understand this, Imagine a galaxy located 1 megaparsec away from Earth. The CMB data suggests that it should be moving away from us at 67 kilometers per second. If the galaxy were 20 megaparsecs away, its speed would increase accordingly. This measurement, however, conflicts with recent observations that show a higher rate of expansion in the present universe, leading to the ongoing debate in cosmology. The universe is expanding at an accelerating rate. At distances greater than about 4,000 megaparsecs, galaxies are receding from us faster than the speed of light. One method to determine this expansion rate uses pulsating stars known as Cepheid variables. These stars have helium-rich outer layers that expand and contract, producing fluctuations in brightness that allow them to act like distant beacons. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid variable is, the slower it pulsates. This breakthrough allowed astronomers to calculate a star's absolute brightness and determine its distance. This method of measuring distance became fundamental, allowing astronomers to build a cosmic distance ladder by connecting observations of nearby Cepheids to more distant ones. To construct this distance ladder, astronomers start by calibrating the closest Cepheids, using their known brightness to calculate distances. Additional rungs of the ladder are added by relying solely on Cepheid measurements. After that, astronomers observe the redshift of light from distant galaxies and stars, which increases as the universe expands. This gives a precise measurement of the Hubble constant, which is key to understanding the rate of expansion of the universe. In 2019, a team led by Adam Rees used the Hubble Space Telescope to observe the Large Magellanic Cloud, one of the nearest galaxies, resulting in a measurement of the expansion rate at 74 kilometers per second per megaparsec. However, this result differed from the value derived from the Cosmic Microwave Background (CMB), which provides an estimate of the universe's expansion rate based on early universe conditions. Some astronomers speculated that the discrepancy might be due to measurement errors, especially in regions with high stellar density. When the James Webb Space Telescope (JWST) launched in December 2021, it was poised to either confirm or resolve this tension. With a mirror twice the size of Hubble's, JWST can observe objects 10 times fainter and is more sensitive to infrared wavelengths, enabling it to detect light from distant galaxies in greater detail. Using data from JWST, Rees's team obtained a value of 73 kilometers per second per megaparsec, very close to their previous result. Other independent methods, such as observations of supernovae and gravitational lensing, also yielded results around 73 kilometers per second per megaparsec. This consistency has left cosmologists grappling with a perplexing problem. According to Ryan Keating, a cosmologist at the University of California, the CMB's temperature has been measured with 1% accuracy, and the Cepheid-based distance ladder is also approaching similar precision. A 7 km per second discrepancy might seem minor, but it's unlikely to be a statistical fluke, suggesting that there may be something more fundamental at play. Three main explanations have emerged: measurement errors, new physics, or a combination of both. One of the most popular hypotheses is that dark energy, which drives the accelerated expansion of the universe, behaves differently today than it did in the early universe. If dark energy was stronger in the past and has since diminished, it could make the universe appear smaller in the early stages, thus leading to a faster expansion rate. There are also other potential explanations, such as the possibility of two different types of dark energy or interactions between dark matter and light. However, these ideas present challenges and require further investigation. Dark energy and dark matter are not the only mysteries that JWST is helping to solve. Its mission includes looking further back in time than any previous telescope, allowing astronomers to observe galaxies formed just 300 million years after the Big Bang. But the early universe is proving to be more complex than expected. While studying the universe's beginnings, astronomers found that many of these early galaxies are much larger and more developed than the standard model predicts. According to current models, the early universe should have been filled with young, hot stars forming at a rapid rate. However, James Webb's observations revealed galaxies with a surprising abundance of heavy elements from earlier generations of stars, and some even showed signs of massive black holes forming at their cores. To summarize the key points: cosmology basics. The Big Bang marked the beginning of the universe about 13.8 billion years ago, followed by rapid expansion. Measuring the expansion rate. Two main techniques are used to measure the universe's expansion. Early universe measurements based on the cosmic microwave background, CMB, and current measurements based on Cepheid variables and supernovae. These methods have yielded different results. James Webb's role. JWST's advanced capabilities confirmed the higher expansion rate observed in current universe measurements, supporting existing discrepancies. The Hubble tension. The difference between early and current universe measurements suggests a need for new theories or refined measurements. Implications for cosmology. The Hubble tension points to potential flaws in the lambda CDM model, which may require adjustments or new hypotheses to account for observed phenomena. Early galaxies and surprising features. JWST's discoveries of unexpectedly large and developed early galaxies challenge existing models, suggesting the need for further investigation and possible revisions in our understanding of the universe's evolution. James Webb's groundbreaking observations continue to shape our understanding of the cosmos, and its findings are likely to lead to major breakthroughs in cosmology, potentially forcing a re-evaluation of many aspects of our current models.